In this video, we are going to discuss three things. Number one, we are going to fix a shape optimization to minimize the maximum stress. In the second part, we are going to construct a multi-objective expression that will minimize both the mass and will minimize the maximum stress. And then in the third part, I'll discuss how to perform the shape optimization for multiple subcases. It's very common that you find a tutorial and it only discusses one subcase or one load case. But then when you have 2, 3, 5, 100 subcases, the process is not so clear. So in this video, I want to point out how do you handle multiple load cases. Now, in the first part of the video, this is what we're going to do. We are going to minimize the maximum stress. So we're basically going to do the maximum of individual stress responses, A1 through A18. And then this is going to work as long as you have a small number of variables and a small number of elements. If you have hundreds or thousands of variables, if you have hundreds or thousand stress values to consider, you are going to have to consider a different stress metric if you want to minimize the maximum stress. But here we're only working with a very simple model. We only have a few variables and a few elements to consider. So we can just go ahead and take the maximum function and use that during our shape optimization. Now, this question originally arose from the following scenario. One of my viewers went ahead and tried to configure a shape optimization, but unfortunately it did not make any progress. Here you can see that the objective did not change, the max normalized constraint did not change, and the variables, the shape variables, also did not change. So now let's go ahead and talk about the analysis model. So here we're working with the cantilever beam. It's fixed on one end, and you can see that we have the load on the other end here at the free end. Now, let's go ahead and look at the stress results of this analysis model. So here you can see that our highest stresses are happening near the root or the edge where the cantilever beam is fixed. Now, intuitively, what can we do to reduce the stress? For this very simple example, we can just add more material in this region of high stress, and when you add more material, the maximum stress should be decreased. Now, when we look at the shapes for the shape optimization, this is what we have. In green and yellow are expand and contract regions. So the nodes, if you will, they're allowed to move, they're allowed to expand and contract in this yellow and green edge. But you see a problem here in this gray edge. These nodes here, they're not allowed to move. You are not allowed to add or remove material here. This is the reason why the shape optimization did not make any progress. Here you're saying do not add or remove material here, but this is actually where we have the highest stress values. So that's a problem for us. We need to have the ability to add and remove material here. So what we're going to do now, let's go ahead and modify the shape. So we're going to select these faces that are going to be allowed to expand and contract. And let's go ahead and generate a preview of our adjustment. Now, what I should have done a moment ago, maybe let me remove those faces from the shape. And let's look at the, right. So here, when you look at the original shapes, you can see that here, you at these nodes at the far left side, you cannot add or remove material. Those nodes are fixed during the optimization. So what we're doing now, we're saying, hey, you know what? I actually do want to move those nodes. So here I've readjusted the shape and you can see that those nodes are now moving. Now, here we have sort of a conflict because we have the possibility of a shape distortion. So how do we address this? These nodes here on these gray faces, they're currently not allowed to move. So what we're going to do is we're going to click on these second button here. So you can see these lighter yellow colors. We're going to select these faces as secondary faces. So just pay attention that we have very dark yellow elements and then lightly colored yellow elements. The dark yellow elements are the primary faces. These are going to be faces that are expanding or contracting during the shape optimization. And then in the lightly colored faces, these nodes are free to move during the shape optimization, or rather they're relaxed, I'll say. So now when we run Nastran to generate our preview, you can see that the mesh distortion that we almost had, it's been alleviated, if you will. You can see that the nodes on these faces are allowed to move in a relaxed manner, if you will. Okay, now let's go ahead and talk about the bounds. The bounds of the variables are very important because they're going to prevent the mesh distortion. Here, let's go ahead and experiment with a shape change of -2 for both shapes. So what happens if the variable changes by -2? Here you can see that if the lower bound is ever -2, we'll most likely get a shape distortion here. So what happens if we use a value of -1.5 for both variables? So what if the variable changes by -1.5? Here we see that we most likely are not going to get a mesh distortion. So what we'll do is we'll take these test values that we used and we'll use those as the upper bound. Or we'll use those as the lower bound for both design variables y1 and y2. Okay, now what happens when we use a positive value for the variable? What happens if we use, I don't know, a 10? Will that cause a mesh distortion? So you can see how significant that change is. You can see some of the elements are becoming very distorted. We don't want that. So what we're going to do is we're just going to experiment with these test delta y's. So here we'll say, okay, maybe that's okay. What about the second variable? What happens when I use a value of 2? Okay, well, when I use 2, it doesn't seem I get a mesh distortion. So what I'll do is I'll copy that value and I'll carry it over to the upper bound of both shape variables. So now through that experimentation, I know what lower bound and upper bound to use, so I do not get a mesh distortion. Okay, let's go ahead and look at the new entries. Okay, this just gives you an idea of what's changed in the bulk data files. Let's go ahead and now download our new set of bulk data files. And let's go ahead and do this. Let's go ahead and attempt to run the optimization. So remember that previously we didn't make any improvement in the optimization because we were not allowed to add material to the region of high stress. But now we adjusted the shapes. We then perform our next optimization. Here are the results of that optimization. And here, let's look at the objective real quick. So the objective was to minimize the maximum stress. So here we see that the maximum stress was originally a 197. But then by the end, we see that the maximum stress is now 21. Here we have some information about the maximum normalized constraint. But let's look at the variables. Here we get an idea of how the variables change during the optimization. But here, what I'm going to do instead, I'm just going to open another viewer. And there's a directory called the workspace B that's created by the Sol 200 web app. And the new model is called model final. This has the updated model for you. So that's what I'm looking at right now. So let's look at this. So you can see that shape 1 was enlarged. So again, the more material we add to the root, to the region of stress, the more material we add there, the more we're decreasing the maximum stress. Now here, I suspect that this second shape was reduced because it was trying to satisfy that weight constraint. We had a constraint saying that the mass should be no greater than 85. So I think that was, the shape was contracted to satisfy that, or to help satisfy that constraint. Okay, so that was the first part of the tutorial. We were tasked with fixing that shape optimization. Again, the issue was that the original shapes did not allow for adding material at the region of high stress. So here what we did is we adjusted the shapes. We now add more material here. We reduce the maximum stress. Okay, now for the next part, how do we configure a multi-objective expression? So let's go ahead and do this. Let's go to the optimization web app and let's go ahead and upload those bulk data files that were used for the shape optimization. Okay, so let's go ahead and do this. Let's go ahead and delete the constraint on the weight. And let's go to the objective section. Let's go ahead and create a different weight response here. We'll click on weight one time and we see that we have a new weight response here. It's called response A19. Here in the objective, let's do this. We'll say that A19 divided by the original weight. For now, I use 1.0 because I don't know what the original weight. Plus the maximum stress divided by the original stress, which is also unknown at this time. So here I'm expressing the mass and the maximum stress as fractional values. A19 divided by the original mass, and then the maximum stress again divided by the original stress. So let's go ahead and get these values of the original mass and the original stress. So the way you can do this, you can open the F06 file and you can hunt down those values. So here, this example happens to be using the output from grid point weight generator capability. So here I know that the original mass is 80. So what I can do here is I can say 80 here. So at the beginning of the optimization, this term is now going to have a value of 1.0. So we'll call this initial. And now what is the initial value for the maximum stress? So again, you can hunt that down by going through this file, or you can use another tool called let's go ahead and see if I can find it. The responses web app. So let's go ahead and look for that real quick. So the responses web app is going to show you the same tables. So all this information, it's going to be put in a table like here, like you see on the screen. So what we want to look for is the DRES2. So here we see that the original value for that DRES2, which was the maximum stress, I had a value of 197.92. So what I'm going to do here, I'm going to replace the value here with the original value. So you can imagine that I'm normalizing the mass and I'm normalizing the maximum stress value. So that's how you configure a multi-objective expression. So let's go ahead and do this. Let's go to the exporter. You can see that I get one error message here. I'll get to that in part 3. So let's go ahead and click download bulk data files. And then in a moment, I'll go ahead and get a new set of bulk data files. So let's go ahead and unzip that. Now here I'm using my Ubuntu Linux operating system. I know a lot of the tutorials are based on Windows or Red Hat Linux. So if you want to do this on Windows or Red Hat Linux, I recommend following the PDF tutorials that I have on the website. Okay, so let's go ahead and see if we were able to run the optimization. So since we normalized both values, what do we expect the I think it was 197. What do we expect the initial values for both terms to be? So we expect both terms to be equal to 1.0. So then what's our total objective? Initial. It should be 2.0. So now if we look here at the results of that optimization, this is what we have. For the initial design, the objective is 1.99. We get 2.0 as we expected. Now let's look at what's happened to the objective. We see that the objective has been reduced from 2 to 1. And let's look at what's happened to our design variables. So by the end, we see that for variable y1, maybe it's changed, maybe not. Sometimes it's really difficult to know what's happened from just the design variable plot, what's happened to the shapes. And let's go and look at our design constraints. Let's make sure this is feasible. Okay, we get a negative maximum normalized constraint at the end. So that's telling us we get a feasible design. All the constraints are satisfied. So what I can do now, I can go to the viewer. I can go ahead and go to that directory. And here, I didn't run this with the web app, so let me rerun this. So when you do this tutorial, you're going to get a Start MSC Nastran shortcut. Click that link or that shortcut. This is going to open up the status page and the results page. It's also going to create this directory, workspace B. And this is going to have the updated model, if you will. So let's go ahead and go to workspace B and upload that bulk data file. Now this is what we expect. We do expect it to increase some of the, or we expect it to add material. And here it's very subtle, but I suspect that it did add material here, and here it's reduced some of the material. What you can do here in the web app also, you can upload the H5 file, and you can look at the stresses just to confirm if in fact the stresses were reduced or not. And here it seems that the stress is more or less the same. You can see the stress is 197. So I suspect it was the mass that was targeted. It saw that it could just reduce the mass here and focus on reducing the mass, and at the same time it's reducing the total objective. So here you might ask yourself, okay, what if I really, really wanted to force the minimization of the max volume or max stress? You can use these additional scale factors. So here I'm just using a scale factor of 100. Here I'm multiplying the second term by a scale factor of 100. You can experiment with the scale factor, so the optimizer prioritizes the second term, which is minimizing the maximum volume stress. Okay, what is there left to do? So let's go ahead and maybe confirm what the mass is at the end. So let's go to the responses web app, and let's upload the F06 file of that optimization. And let's look at the weight response. So here you can see that the initial mass was 80. And then by the end, the final mass is about 53.899. So we did reduce the mass a lot. Now, let's see if we can look at the stress. Here we see that the maximum stress is happening in element 61 and 71. So let's go ahead and do this. Stress, and let's see if we can look for it. Element 91, element 91, and then some other stress values. All right, so these are going to be the other ones. Okay. So here we're looking at element 1. So I'm looking at these rows, response A1, A2, and so on and so on. So what I can do here is I can look at maybe A1. Or actually 1.97. Let's see if it's here. Okay, so let's look at response A3. So here for response A3, we get 197, and then at the end we get 6.17. So let's go ahead and confirm those. So right now we're looking, oh, right. I got my bearings mixed up here. So right now what we're looking at the stress for the initial design. If you look at this table, the column design cycle, right now I'm looking at the first row, which is design cycle 0 for subcase 100, the 0 indicating the initial design. So here, what I would do is I would mark the checkbox for this row, design cycle 16. So let's go ahead and do that real quick. Let's look at maybe the MSC stress for the corners. Oh, okay. So here, this is where we actually see the stress did change. So again, ignore everything I was looking at here in the responses web app. Ignore everything I was discussing here in the table. Part of the confusion was I was looking at the wrong design cycle. So here we're looking at the final design. So we see that the maximum stress was happening here, but we added more material here, but we reduced the material here. This caused the peak stress to actually move to this region. So that's what it looks like. Here, if you want, you can turn on the labels and see where the maximum stress is at. It's at element 67 and element 7, as you see here on the screen. Okay, so here I think we've confirmed that we were able to at least relocate the maximum stress. Now, I should mention that one of the motivations in trying to minimize the maximum stress is you're trying to achieve what's called a fully stressed design. This is where you have as many elements as possible being equally stressed. When you have as many elements as possible are equally stressed, you're efficiently using your material and your structural design. Now, for this example, that's not possible. Part of the reason that's not possible is because here you can see that the way you reduce the stress in this example is you just keep expanding or increasing the depth of the beam. So you add more and more material here and here near the root, and then that will minimize the stress. That's not really possible, in my opinion, for this cantilever model. If you're dealing with an axially loaded bar or plate elements that are subjected to in-plane loads, that's where you could have a so-called fully stressed design. So here, let me sum it up. One should not expect every element to be equally stressed. But what you should expect 2 or more locations where you have peak stresses. If you have 2 or more locations where you have a peak stress, that's indication that you are getting a more efficient design than before. Here we do get 2 regions of peak stress here at the top and the bottom of this cantilever beam. Let me show you another example where this was done. Let's go to theengineeringlab.com and look at this shape optimization tutorial. So here is an example where we use machine learning. This is an example where we use machine learning to go ahead and perform the shape optimization. Here are the results of this shape optimization. So here's another example where every element is not going to be fully stressed. Not every element is going to have the same equal stress. Here, what happened in the initial design, only this region, let me think for a moment. I think it was this region. It was only one region initially that had a peak stress. So we went ahead and changed the radius of this ellipse, if you will. And then by the end of the design or the optimization with machine learning, we now have 2 regions. If you look at the bottom right, we now have region 1 and a second region of peak stresses, whereas before we only had 1 region of peak stress. So again, if you have 2 or more regions of peak stress, whereas before you did not, that's indication that you were able to actually improve the design. So again, you should not expect every element to have the same equal peak stress, but you should expect at least 2 or more locations with equal peak stress. And here we do. We have equal peak stress at the top and the bottom. Okay, so that was the second part where we were configuring a multi-objective expression. Let's talk about multiple subcases. So if we look at the original analysis model, we have two subcases. Now, how do we do that in the web app? So let's go ahead and look for the web app real quick. So when we go to the subcases section, we have two columns here, subcase 100 and subcase 101. You can just mark these checkboxes one by one. You can click one of the yellow or green buttons to adjust the checkboxes, or you can press and hold the shift key and hover over the checkboxes to make your selection. So if you had 10, 100 subcases, you can just use these simple buttons to make your selections and assign your constraints to the various subcases. I know that becomes a very tedious task when you're manually typing that out in the bulk data file. Here, if you want to save yourself the 20 hours, the 12 hours of work, and you want to just spend 2 minutes doing that, you can use the checkboxes here. Now, here, when we configure our multi-objective expression, when we have multiple subcases, we have a problem. A1 through A18 are element stresses, but then the Nastran program is going to come back at you and ask one question. Hey, you have two load cases. From which load cases are these stress responses coming from? And you say, okay, all these stress responses are coming from subcase 2, or all these stress responses are coming from subcase 1. So what you can do is the following. You can go to the DR span table here in the bottom left, and you can say, okay, response A1 is coming from subcase 100. Response A2, all these responses are actually coming from subcase 100. So you can go ahead and mark all these options. Now, what you can do, alternatively, you can leave them all blank, and I believe Nastran will assume those responses come from the first subcase. So I believe that's what we did actually. We left them all blank. Nastran assumed that they all came from subcase 1, which is the statics analysis. So you use the stress responses from subcase 1 to compute the combined objective. But if you wanted to consider a different load case, that's easy. Just select the different subcase numbers like you see me do here on the screen. And let's go ahead and do this here and here. And then I believe what happens, let's go ahead and zoom out of here. Let's see if I can show you. Okay, so here on the top right, you see what's changing. You see that there is a DR span statement in here somewhere. So let's see if we can track it down. Here. So you can see for subcase 101, we now have a DR span statement. So let's zoom in so this is a little bit more clear. So you see that we have the DR span command. It's pointing to set 30,002. So let's go ahead and find that set. And here's the set. So set 30,002 is pointing to the DRESP1 IDs. So DRESP1 6,000,001, 6,000,002, and so on and so on. So these DRESP1 IDs are the individual stress responses for the elements. So response A1, A2, A3, and so on and so on. So that's how you handle multiple subcases. Again, I know a lot of tutorials are just going to focus on one load case. But then when you're tasked with multiple load cases, you don't know what the process is like. But here in this tutorial, we handle at least two load cases. We talked about assigning constraints to multiple load cases. And then what do you do when you're tasked with a multi-objective expression where the responses could come from multiple subcases, if you will. And then once you're done configuring this, you could just click download PDF and go ahead and perform your optimization. Okay, so that was this quick video. Again, what I wanted to do was the following. I wanted to fix this one shape optimization where the goal was to minimize the maximum stress. The original problem was that we were not allowed to add material at the root, the fixed end, where the maximum stress was located. Since we cannot add material there, we could not minimize the stress. So what we went ahead and did, we modified the shape. We allowed the ability to add material there, and then we were able to make improvements during the optimization. In the second part, we wanted to configure a multi-objective expression. We wanted to minimize both the mass and we wanted to minimize the maximum stress. When we went ahead and looked at the stress responses, we saw that we were able to minimize the stress at the root, and then the peak stress actually moved to a different location in the model. And then for the third part, I wanted to show you how to handle multiple load cases. In this case, we were dealing with 2. So yeah, that's the end of the video. And just in case you do have questions, I'll go ahead and leave my email address here. If you have a question regarding shape optimization, or you want to minimize the maximum stress, feel free to contact me at this email address, and I'll try to get back to you as soon as I can. So that's the end of the video, and as always, thank you for watching.